Thank you for coming. So I'll speak about our work on inter-sentence relation extraction with graph convolutional neural networks. So a little bit about the task. So relation extraction is essentially the identification of relations between name entities, and it can be considered as two types of extraction. So first is entity-based extraction, where we have two types, mention level and concept level. In the first level, we considered each name entity uniquely. So as you can see in the example, oxytocin, oxt, euteronic, or hypotension are considered for different entities, whereas in the concept scenario, multiple entity mentions are mapped to the same concept. So here, oxytocin and oxt are considered as two mentions of the same concept, oxytocin. In the second scenario, we have context-based relations. So intra-sentence relations are between entities that reside in the same sentence, where inter-sentence ones are between entities in different sentences. Again, as shown in the example, oxt and euteronic have an intra-sentence relation, while oxt and hypotension have an inter-sentence relation. So generally, we can identify intra-sentence relations using local dependencies that reside within sentences, and this was proved by previous work to be adequate for intra-sentence relations. However, for inter-sentence relation extraction, we have to rely on non-local dependencies, such as coreference or discourse type of dependencies that are residing across sentences. So as you can see in the example, again, in order to identify the relation between oxytocin and hypotension, we need both local and non-local dependencies, such as coreference and some kind of syntactic dependencies. So our main idea was to simply combine local and non-local dependencies at the same time. Essentially to represent a textual snippet, which is typically more than two sentences as a graph structure, and use the words of the structure as the nodes, while edges correspond to local and non-local dependencies between them. We also aim to incorporate the graph convolutional net for graph encoding and use multi-instance learning to perform concept-level relation extraction. So to formalize the task as inter-sentence concept-level relation extraction, the input of our systems are two concepts, C1 and C2, their corresponding mentions that can be more than one, and the textual snippet T. And the output of the system is the relation R between concepts C1 and C2 for this particular snippet T. So let's move on to the architecture. So the input of the model is our named entities with their mentions. So here the first concept is oxytocin with two mentions, and the second concept is hypotension with one mention. We concatenate the word representations with relative position representations in the input layer, and we particularly use the closest position, so we use the position to the closest target mention. So given that, we feed this structure and we try to create a graph from that. So again, as I mentioned earlier, words are nodes and edges are semantic, syntactic, or sequential kind of dependencies between the nodes. So essentially, I try to encode both intra and inter sentence information. So we split the kind of edges in local and non-local ones. So starting with the local, first we use syntactic dependency that can help us have informative clues for intra-sentence relations. Then we use adjacent word information as followed by previous work. So essentially we combine the next and the previous word to the current word in order to encode some kind of sequential information into the model. And finally, we use self-node information. So we want to have information about the word itself into the model. So we include this type of edges as well. And for the non-local dependencies, the first type is adjacent sentence. So in a very naive effort to encode discourse dependencies, we connect each sentence to its previous and the next one based on the root nodes. So we first identify the roots of this sentence and then connect previous and next roots. And finally, we use coreference. So coreference can be helpful for both intra and inter-sentence relations. So if we find co-referring mentions, we also connect them with an edge. Moving on to the encoding, we use a graph convolutional net to encode that. So this is nothing new. I mean, proposed by Marchayani and Titov. We especially use K-stack GCN blocks to encode information from neighboring nodes, and L different type of edges, which is essentially L different number of parameters in the GCN. So in order to avoid overparameterization, we tune the number of parameters and keep the top and most frequent edge types while merging all the remaining types as a single name-reared edge type. And the final layer of our network is a biaffine layer. So here, what we're essentially trying to do is to combine mention-level information into concept-level information. So we first map each word to two different spaces using two-layer feed-forward neural networks, depending if the word serves as the first or the second argument of the relation. And then, after we have these two mappings, we use a biaffine pairwise scoring function to combine information from multiple mention-level pairs into a single concept-level pair. So this gives us a final score for each relation type for a given concept pair. So moving on to the data sets we used, so we applied this in particular for chemical interactions. The first data set is the CDR data set, a manually annotated gold data set with abstract level annotations, with chemical disease relations. And we also developed a new data set, which is distantly supervised for interactions between chemicals. So in order to create this data set, we essentially used abstracts from PubMed and identified chemicals using the Thalia search engine, which we aligned with the Pygame4J knowledge base. So overall, we were able to collect almost 30,000 positive interactions between chemicals. Very briefly, the tools we used NG dependency parser for syntactic parsing and Stanford for reference, as well as the linear taggers and splitters for sentence splitting and tokenization. We also compare our approach with two baselines, a CNN encoder and an RNN encoder, which are essentially reimplementations of previous work. So we adapt these two baselines to use biaffine pairwise scoring as their final layer to compare with GCN. So moving to the results, for the CDR dataset, our model is the third best model compared with other systems that do not use additional enhancements. And for the CHR dataset, we were able to overcome the performance of the CNN and RNN encoders. But moving to the analysis, we first tried to see what is the optimal number of edge types. So we saw that the top 4 different edge types perform best for our model, indicating predicates and adjectives as being the most frequent type of edges. And we also tried to find what kind of dependencies are useful for the overall intra or inter-sentence performance. So generally, as expected, intra-sentence relations are mostly relying on local dependencies, such as syntax or word order, but inter-sentence relations were both influenced by all kinds of interactions, so both local and non-local. So just to summarize, we proposed a graph convolutional net for inter-sentence relation extraction and built a chemically based corpus using distance supervision and tried to see the effectiveness of local and non-local dependencies for inter-sentence relations. So as future work, we aim to incorporate more enhancements in the model, like joint linear training or subword embeddings, as well as apply the model to different domains. And you can find the corpus here. So thank you.
All right, we have